Okay, good morning everyone and welcome. Before we have our chat about C++, I would like to give you a quick disclaimer. I've been in America for only a couple of days, excuse me, and as such I'm still a little bit jet lagged and still a little bit Australian. As such, I'll make every effort to speak clearly, but I simply cannot guarantee that everyone will understand everything that I say. So with that disclaimer out of the way, my name is Bowie Owens. I work for CSIRO, which is Australia's government-funded research organisation. I have a little over 20 years of industry experience programming in C++, and I'm pleased to be here and able to talk to you about expression templates today, because this is a topic that has been a pet project that I've revisited a few times over those 20 years, and I found it interesting each time. Now, my domain is finance, but it's a technique that has application in many other domains as well. But the one thing that I've learned about expression templates from writing this talk is that 30 minutes is not a lot of time to explain expression templates. So we better get moving. I'm going to begin by showing some of our code before we changed it to use expression templates and discuss the motivation for that change. I'll introduce expression templates and their relationship with operator overloading. Then the majority of the talk is going to be how I have implemented expression templates, but with an emphasis on how C++ 17 makes this easier than ever before. And then I'm going to conclude the talk with a brief summary and some links to related talks that I think are helpful. Okay, legacy structure. Be warned, the next slide features code that some may find disturbing. This is a real statement that was present in our code. Note that the line breaks were introduced by PowerPoint when I copied it in. The function being called is tridiag scalar sum 4. It takes 4 tridiagonal matrices, 4 corresponding coefficients. It multiplies the matrices by the coefficients, sums the results. The tridiagonal matrices are passed in as 3 separate arguments, one for each diagonal band of the matrix. The result is then passed back out by 3 separate output arguments. Now, this code actually has 2 nice properties that I'm going to come back to, but nonetheless, I had some problems with it that I wanted to resolve. First of all, it's difficult to read. I hope we can all agree on that. That makes it difficult to reason about. It's also concealing. The difficulty to read and reason is concealing opportunities to improve performance, and it's also difficult to modify. So what can we do about these problems? Well, as C++ programmers, first port of call would be to write a class that represents the tridiagonal matrix. And then we would create an easy-to-use interface using operator overloading so that we can write expressions on those classes. Now, it should go without saying that we're going to need tests, but I'll say it anyway. Whenever we're going to refactor code, we should have some tests to make sure we don't unintentionally change the behavior. The strategy for testing that I use is essentially equivalent to Claire McRae's approval testing. I've given a link to her talk at CPP on C, and I noticed she's actually in the room today, so that's nice. I do recommend this talk. Okay, so with our tests in place, we can start changing the code, including the formatting. This makes the code easier to read and therefore easier to reason about. For instance, you can start to identify things like temp1 logvol is both an input and an output of the operation. And now that each matrix is a single argument, it's easier to modify, easier to add and remove sub-expressions. Unfortunately, this change has made the code worse in 2 measurable ways. So how have we made this code worse? Well, to make that explanation a little bit simpler, I'm going to shorten the names and the expressions to create a more manageable example. Okay, so this code is equivalent to the preceding code in enough ways to illustrate the problems. So, how have we made the code worse? We've introduced temporaries. Each operator in the expression will become a function call which returns a value into a temporary. Now, we can take advantage of move semantics to eliminate some of the copies, but there is no convenient way to eliminate all the copying. Why is this so much worse? Well, for all its faults, tridiag scalar sum 4 did not allocate any memory, and it did not throw. The temporaries, on the other hand, are going to allocate memory using standard vector so that they can store the intermediate calculations. And introducing even a single allocation is going to make things worse by, one, allocating memory is time consuming. For our matrices, the main diagonals have in the order of a couple of hundred elements, and the allocating memory leads to a roughly 12x slowdown, which is important because this is part of an inner loop of our code. The second problem is that allocating memory may fail. So we have moved from code that was no accept to code that may now throw. Okay. So how can we get the clarity that we want without the performance degradation or risk of throwing? We need a way to perform the entire calculation all at once, the same way tridiagonal scalar sum 4 did. Expression templates are going to give us that power. And so now we'll look at an overview of how expression templates relate to operator overloading. And once we have that overview, then we'll move into the implementation details. Okay, so we cannot get rid of the temporaries. So what we can do, however, is create classes so that the temporaries are cheap to construct, but record the work to be done. We alter the operators that we have defined so that instead of performing the intermediate calculations, they return objects of these classes. Now, throughout the talk, I've tried to highlight the code that has changed or is most relevant in blue. But that's all that means. Okay. Now, also in this case, I've written out the signatures by hand so as to introduce the idea, but in reality, we're going to need to write templates, of course. So let's have a look at what this change does to our simplified example. Okay. So now we have cheap to construct temporaries that do no work, but instead they represent the work to be done. We delay actually doing that work until we have the complete expression, including the destination. Then we can evaluate everything efficiently. So this is the essence of expression templates, batching up work until it can be done efficiently. Okay. So how do we implement these classes and functions in C++17? And what features make it easier than ever before? So that's what we'll move on to now. Okay. So the expression objects have two primary jobs. First, they must store the information needed to perform the operation, and the type of that information is going to vary, so we're going to need a class template. Note that while I have spelt the name of the template as EXPR, I'm probably going to pronounce it as expression. I hope that's not confusing. Okay. So, first, we're going to record the action that must be taken to perform the operation. This is done by storing a callable object as a data member, which I've called f underscore. Okay. Now we'll also need to store the operands or arguments for the operation in a standard tuple, holding its components by reference. Now, for an enjoyable discussion of the pronunciation of standard tuple, I recommend Guy Davidson's talk at C++ on C earlier this year. Now, we are using reference semantics because we wish to avoid copying, but using reference semantics means that we have to be careful not to keep a reference to a temporary past the end of its lifetime when we start writing expressions. Okay. I've used a variadic template so that the one template can represent unary operators like negation and binary operators like multiplication, or in fact any other arity operation. Okay. So what this does is it mitigates the need for the curiously recurring template pattern you may have seen in other expression template libraries. Okay. And lastly, we have a constructor that takes all the necessary information and stores it into the object. Okay. Once we have the ability to construct our expression objects, our operators, operator functions, do nothing but call the appropriate constructor. Note that I handle scalar types like double and matrix types uniformly at this point, so that we only have to define one multiplication operator function. We do need to discriminate between scalar and matrix types at some point, but I'm not doing it here. Discriminating between scalars and matrices at this point often leads to writing the same multiplication operator function 3 times. Once for scalar by matrix, once for matrix by scalar, and once for matrix by matrix. This way we only do it once. Now C++17 has auto return type deduction, so that we only have to specify the type in the return statement. This avoids a redundancy that was necessary in older C++ standards. Okay. C++17 also has class template argument deduction, which is why we do not need to specify the type arguments for the expression. This eliminates a further source of redundancy that was required in all older standards, making the code much neater. Okay. So we're going to pass the parameters, left-hand side and right-hand side, through to the constructor without interfering in any way. And then how do we define mul? I prefer to use a lambda so that everything is located in the one place. Note that this is, the function object is going to be operating on the elements of the matrix. So while using a lambda cannot prevent mismatches like the one in this slide, at least you have the best chance to spot the error. The time that I made this mistake, the coworker who found the bug was not happy with me, I can assure you of that. So now wasn't planning on showing the other operators like addition and subtraction, so I hope you can infer what they would look like from the multiplication definition. And now, this is a generic lambda. So it has auto parameters, so that we don't need to care about what types are going to be multiplied with it later. Although in my example, they are simply doubles. Okay. The lambda also has a deduced return type, so that we let the compiler work out what type L times R has. This allows the code to work correctly when L and R are, say, strongly typed distances, and therefore L times R would be an area. Getting this to work without return type deduction in the past was somewhere between miserable and impossible. Okay. Now, in the above code, the type parameters left-hand side and right-hand side are unconstrained. This allows us to call the operator with any 2 types. This is good in that it allows the one operator, as I mentioned, to handle scalar by matrix, matrix by scalar, and matrix by matrix. Unfortunately, it also lets you multiply objects that have no business being multiplied. Okay. So how do we prevent this? Okay. So we can prevent operators working on unintended types in C++17 using svna, svna being substitution failure is not an error, or if we have C++20, we can use concepts. Okay. So what we need to do to begin with in either case is to construct a predicate on the left-hand side and right-hand side types. That is true for acceptable pairings and false otherwise. An acceptable pairing being at least one of left-hand side or right-hand side being a matrix or some other expression object. So in this implementation, I have used a const expr bool is binary op OK for each combination of left-hand side and right-hand side. And I simply have to set that to be true in the cases that I want. So I've left out that definition because it goes for a while, and I'm not sure it's that helpful, but I have included it in essentially an appendix section to my slides, which if we have time and people are interested, we can look at later, or you can download after the conference. Okay. Now, for sphenae, we use an unnamed type parameter with the default value involving standard enable if to enable our operators only if that predicate is true. Okay, so the only C++20 I have in this talk at the moment is this slide. So with C++20 concepts, we can use requires instead of sphenae. Essentially does the same thing, but it's a bit nicer syntax. Okay, now the second job that the expression objects have is to calculate the values on demand. To give some context for the implementation of the calculations, note that this is what we're aiming for. We want to make these two fragments of code equivalent. So we're going to be doing multiplications by a scalar and then additions, and these operations can just be done as component-wise operations on the elements of the matrix. So this is what we're aiming for. How do we get there? We're going to invoke the calculation inside an assignment operator on the destination object. So let's start there. We perform calculations with the code, that appears as if we are copying an array. The operator square brackets on v underscore provides the place to store the result of the calculation. Note that in my implementation, I don't call resize on v underscore. Instead, I assume that it's properly sized before the assignment because I want to, in my particular case, I want to make absolutely certain that I'm not doing any allocations during assignment. I also use the size of v underscore to drive the loop in case the source object is of a type that we might not want to give a size to. For example, if you wanted a special type representing the identity matrix, which actually doesn't store anything at all, but simply returns 0 or 1, depending on which index you ask for. Okay. So the operator square brackets on the source object is the piece that is actually going to do the calculation for each element. Okay, so now we need to define that operator on the expression type. Working top down, so we start by calling standard apply, which takes a function and a tuple. Standard apply calls the function, breaking down our args underscore tuple into individual arguments. This is a really convenient way to get all the components of a standard tuple. The function that standard apply calls is a lambda, which will subscript each individual argument A with index I. Note the use of expansion by ... so that in the case of unary operators, this is going to expand to one call to subscript, binary operators 2, and so on. Okay. Now you might be wondering, why do I call subscript instead of just having square brackets I after A? Okay. So earlier I mentioned that scalars need to be handled differently at some point. Doing so here permits operands that are scalar types, such as double, to participate without being boxed inside an object that makes them seem like an array. And of course, in C++17, we have const_if that allows us to introspect on whether the operand is a scalar or a matrix and do the right thing in the respective cases. So when we have access to the indexing operator, we return the ith element, and when we have a scalar, we simply return that scalar. Okay. Then we're going to pass the results, so that's why we call subscript. Then we pass the results of subscript to our function f underscore, which will finally do the calculation. Since the arguments are already broken down, we can call the function directly. Okay, so combining the last couple of slides together, we can see that since operator square brackets calls subscript, and then subscript potentially calls operator square brackets, this gives us recursive traversal into our sub-expressions. Thank you. With those functions in place and a few others that you'll have to imagine, we have that the two fragments of code are now equivalent. So think about this. We have essentially invisibly inserted a loop into our code because of the types of capital A and capital B. Now, if I picked a 1 hour session and that clock said a lot more than it does, I'd spend the next 30 minutes talking about how loop insertion allowed us to change code that was only ever designed to operate on individual values to work on vectors of values by changing the types involved, but none of the expressions. Okay, so perhaps that's something to think about how you might be able to use that in your own code bases. Okay, so I'll just try and wrap up quickly, and then we should have a few minutes for questions at this rate. Okay, so expression templates are not a recent discovery, but in the past the code to implement them was brittle, complicated, and repetitious. One of the reviewers for my talk proposal described them as beyond ugly in C++03 and still clunky in C++11, and those are accurate statements. But the C++17 language features allow the compiler to deduce far more from your code, which eliminates repetition. Vocabulary types and associated functions minimize the amount of code that need to be written. Lambdas allow code to be situated more conveniently. And in C++20, concepts will further improve matters by replacing sphene and improving the readability of templates. Okay. So where can you learn more? I do recommend Guy Davidson's talk at CPP on C for more than just the pronunciation of standard tuple. It also included a very clear explanation of expression templates. Joel Falcu gave a very comprehensive explanation of expression templates at CppCon in 2015, and as I understand it, spoke again this year on expression templates, but I don't have the URL for his slide, of course. And Jason Turner's C++ Weekly series includes some videos with great examples about how C++ has evolved. I understand he's got a C++17 talk or video coming, but it wasn't out in time for this talk. Okay. So I'm aware that there's some really strong talks on at the same time as mine, so I thank everyone for coming and listening to my talk. And to everyone who was at the conference but is watching later on YouTube, I completely understand, and I thank you for your interest as well. So we have time for questions. Please use the microphone. Please.
In your, you have seen a general purpose expression template. How does it apply in your company? I mean, financial risk and optimization.
Sorry, can you repeat that? I didn't.
how do you use that code in your company for financial risk analytics?
Oh, okay. So there's a number of mathematical models in our software that represent market conditions, and you need to be able to essentially solve PDEs or similar systems of equations to understand how the market is going to evolve over time. So you're trying to, because we do pricing for financial options, which you're interested in pricing something that is going to be valuable to you in the future. So you need to evolve your understanding of the market over time so as to be able to price the option in the future. So we have a lot of mathematical code in our code base. We're not, because we're not doing algorithmic trading, we want to have code that is fast but also readable so that we can adapt it as an improved mathematical model might be published.
And the second question that you have, porting this code to modern C++, have you gained in performance?
Sorry, I forgot to repeat the first question, but this one was, when porting to modern C++, have we seen an improvement in performance? The answer is yes. There's two factors. One of them is that having the code more readable allows us to reason better about things and identify inefficiencies in the expressions. So in the example that I gave, we're multiplying an identity matrix. So we end up doing a lot of multiplications by zero. So if we reorganize the expressions, we don't have to do all those extra multiplications by zero. Yes?
You said for the same expressions, you were able to support scalar values and multiple values. Were you able to have vectorization, like SIMD calls being generated by the compiler or manually with these multiple values?
Okay, so I was asked whether the compiler was able to do, or whether we were able to do SIMD vectorization or things like that. I must confess, I haven't looked at that closely. And it is something I would like to look into. So I'm sorry I can't give you a definitive answer on that one.
Yeah, I just had a question on how you've handled basically anything that's auto, or like if you're capturing a result of your expression template by auto and you get the expression template instead of what it should resolve to, how have you handled those kinds of issues?
Yeah, so the question is, if I have A times B and I then store that to a variable that is declared as auto, so I get an auto inferred type, the type that will be inferred will be the expression rather than the result of the calculation. So you have to forego using auto essentially in those places. And you also have to be kind of careful with, returning from a function as well. So an auto deduced return type, you have to be careful. So typically you just have to give up using auto in that case and know the type that it's supposed to be. And yeah.
Have you noticed any cost in terms of like compilation time of using this?
I have not. So the use that we have of expression templates is fairly surgical. So because we have a legacy code base, we needed to construct our types to drop in to a small, or change a small area of code as possible, and then use them incrementally. Okay, so in our code base, the expression templates that I've been talking about don't seem to add much to compile time. We do also use eigen, and that is probably one of the more term-consuming sections of our code to compile. But for us, the benefits greatly outweigh the cost. Okay. So if there are no more questions, I'll just wish everyone safe coding.